Hello everyone, this is Doug, and in this video we're going to talk about enthalpy some more. In the previous video we talked about the energy that it takes to change phases, and in this video we're going to talk about the energy that it takes to change temperature, right? When temperature either goes up or goes down, what is that change in energy? What's that change in Q or that delta H, right? So let's take a little closer look. Right, we said last time that the change in enthalpy is just the heat that's either released or absorbed from a process, right? Making it either exothermic or endothermic. You should remember those terms from last time. And in the previous video, like I was saying just a second ago, we talked about the phase changes. Now we're going to talk about the temperature changes. So we're going to have equations that look more like this, where Q, right, so that change in enthalpy, that heat that's being released or absorbed, is going to be equal to like the mass times the specific heat times the change in temperature. And we'll see that it also could be moles or something in a second, but this is what we're going to focus on in this video, right? How can we calculate how much energy it takes to heat something up, or how much is released when you cool something down? So temperature changes, right? In order for a substance to change temperatures, heat must be gained or lost. And I want to just take this moment right now to kind of differentiate, right, and really emphasize that heat is not temperature. To the normal common person, right, heat and temperature sound a lot alike, like almost that they're interchangeable, right? You heat something up, the temperature goes up. So heat and temperature must be the same thing, right? Something with high temperature must have high heat, something with low temperature must have low heat. That is not true. That they're different things. They're related, but they're different. Right? Remember that heat is a transfer of energy. Right? Heating is a process. Heat is when you transfer energy from one thing to another. Nothing has heat like things have temperature. Heat is a transfer between two objects. It's how or a process in an object, for example. So it's a transfer of heat. Let me write this up. Oops. A transfer of energy. Now, temperature, right, we said was proportional to the kinetic energy. Temperature is related to the average kinetic energy of the particles. Right? Higher the temperature, the faster the particles are moving, whether it's in a solid, liquid, or gas. And so certainly if you want to increase the average kinetic energy, if you want to increase the temperature of something, you need to supply it with energy so that that energy goes up, that kinetic energy goes up. And you might do that with heat or other processes. But something can have a temperature. You can measure the temperature of an object by just sticking a thermometer in it. You can't measure the heat directly. You have to see that there's some other change going on, like melting or the temperature dropping or increasing or something like that, right? So heat is a process. It's a transfer of energy. Temperature is a property of a substance. How hot is it? Now, what we're going to see for this whole video is that we're going to see one of two different phase change equations. They're either going to look like this first one up here, where we're going to have Q, right, which we know is heat. M is just going to be the mass, so that's usually in grams or kilograms. And then you're going to have a C sub S or a C sub P. Either one, they're both the specific heat. This thing called the specific heat. And then delta T is just the change in temperature. And I wrote this other equation over here, Q equals N times the specific heat or the change in temperature, where N is just like we saw with the gas laws, N is just moles. And that's because when you look up these specific heats, you can find they'll be on the back of your textbook, they'll be online, but specific heats will either be in units of like per grams or per moles. So you'll have one of these two derivations of the same equation. You're just going to make sure that the units match. So like over here on the right-hand side, I have this table of different substances. They're CPs, right? It doesn't really matter what the P or the S is. The idea is that it's a little c, which stands for specific heat. And they have all these values, and they tell you that the units are in joules per mole degrees Celsius. So this would be per mole. That means I'd use this equation over here on the right-hand side where I have mole in here, right? Remember, you need to get units to cancel out always. The units need to make sense. So just pay attention to, and we'll do some examples in a second, but pay attention to, is your specific heat in units of moles per mole or per grams? And I will show you examples of both, not in this video, but in future videos. I'll show you definitely versions of both. So you'll either see this you'll have the relationship between heat and change in temperature that goes through this specific heat, or you'll have this equation down here which relates the heat, right? This transfer of energy to a capital C, not a lowercase c like above, and the capital C is the heat capacity. And then delta T is change in temp again. And I might as well mention this here, right? Remember that delta anything, change in anything, is always final minus initial. Right, so you take the final temperature, subtract it from the initial temperature. And so let me take a minute here to talk about the differences between specific heat and heat capacity. They're similar, they're related, but they're different. So specific heat versus heat capacity, right? I just showed you these two equations here, where we said that you're going to use either of these two for specific heat, right? That's the specific heat. That's the specific heat. The one on the left is for when you have mass, so you're doing grams. The one on the right is for when you have moles. Just, again, pay attention to if your specific heat is given in grams or per mole. Now that's versus the heat capacity here, which again is this capital C. Now both of these equations function the same. The difference is are you going to use specific heat or heat capacity? Specific heat is an intrinsic property, right? And you may remember what this is from like first chapter Gen Chem or high school chem or whatever. Intrinsic property is a property of something that doesn't matter on the amount of something. So intrinsic properties are things like color, right? It doesn't matter. The color doesn't change depending on how much you have of something. The density doesn't, right? The density of something doesn't. The solubility, stuff like that. Right, the solubility is a property of, how soluble is something in water or whatever the solvent is. But it doesn't really matter if you're talking about like 1 gram of salt or a huge amount of salt. It's still, it's still true that however many grams dissolve in a liter is going to be true for any amount of that stuff. Same thing for the density, right? If you're saying the density of water is 1 gram per milliliter, that's true if you have a 5-gram sample of water. It's also true if you have a kajillion gallons of water. It still has a density of 1.5. Or I'm sorry, it's 1.0 grams per milliliter. And also specific heat is. Specific heat is also an intrinsic property. If you say that silver has a specific heat of blah, that's true for a small amount or a large amount of silver. It's going to have the same specific heat because it scales with the amount of thing that you have. Now that's going to be different than what we're going to see for the heat capacity. Heat capacity is an extrinsic property, like things like volume, mass, stuff that changes depending on how much stuff you have. So heat capacity is an extrinsic property. Heat capacity is a property of a specific object. So heat capacity is for a specific object, right? So like you might have a heat capacity for a gold ring, for example, like maybe your wedding ring or something like that. If you have you're going to have a heat capacity for that specific gold ring. And what we're saying is that for your specific gold ring, it's going to change temperatures with a certain relationship to the energy you put in, right? So if you put in 40 kilojoules, you're going to raise the temperature 2 degrees Celsius, for example. But that's of your ring. That is not going to be true of all gold samples, that if you put in 40 kilojoules, it's going to raise the temperature 2 degrees. That's not true of all gold samples because it only applies to your specific gold ring, because your gold ring has a fixed amount. You go to somebody else's gold ring, it might be smaller or larger, and it's going to have a different heat capacity because it will be able to have a different amount of energy in it. Another way to look at heat capacity is kind of like the name says, it's what's the capacity for that thing to have heat, right? Like imagine that you were in a sleeping bag and you had to sleep with a hunk of iron that was at negative 20 degrees Celsius, right? Freezing cold hunk of iron. in your sleeping bag. Now, do you want a huge piece of cold iron in your sleeping bag or a little tiny speck of freezing cold iron in your sleeping bag? Probably the little one, right? Because it's smaller, it has a smaller heat capacity. It doesn't have the ability to absorb a bunch of heat. But the giant piece of iron is much bigger. It can absorb way more heat. It's going to freeze your little buns off, right? It is going to cool you down like crazy because it's so big and it has a higher heat capacity. That's what I mean by it is a extrinsic property. The heat capacity changes depending on the size of the thing, right? And it's for a specific object. You could calculate the heat capacity for your little tiny grain of ice cold iron or your really giant big block of ice cold iron. They'd have different heat capacities. And again, so an intrinsic property would just be, well, what's the specific heat for iron? And that's going to be a value that would be true for all of iron, and it actually relates the heat capacity of your little speck and your big piece of iron, right? So specific heat does not have mass in it, right? You look at the units here. It's joules per degree Celsius and times mole or grams. It could, like I said, there could be either grams or moles here. This could be grams. I'll put or moles or grams. Now, for the heat capacity, those units are just going to be joules per degree Celsius, right? There's no gram relationship because, again, it's just for a specific object, so you already know what the object is. No need to like weigh it out or anything like that. So that'll be another hint as to which one you're looking at here, right? Specific heat has an amount in it, moles or grams. Heat capacity does not. So specific heat is for this is an intrinsic property. It's going to be for any given substance of that type. Heat capacity is for a specific object. So this will be true for one thing that you're looking at. So let's try to apply these concepts a little bit. So, I put phase change in here. That's my bad. This is temperature change. And that's probably going to say that on all these slides. Temperature changes. Right, so let's say we have a question like this. How much energy is needed to raise the temperature of 568.0 grams of water from 20 degrees Celsius to 49.9 degrees Celsius? Right, so if you hear a question that's like, how much energy to raise the temperature, something like that, you should immediately be thinking, oh, that's going to be my Q equals either MC delta T or NC delta T. Let's put MC delta T or NC delta T. And remember that M is just going to be for mass, so you're going to have grams here, or N is for moles. And what you're going to do is you're going to pick which one based on what your specific heat is going to units are. My specific heat units for this table that I'm giving you right now are per mole. So that means I am going to use the bottom one that has the per moles. I'm not going to use the one up here that has grams in it. Now, if I look at my question, it says that I have 568.0 grams of water. But I just said that I need moles because this is in moles. So it's because my specific heat is in moles, I need to plug moles in here. And that's not a big problem, right? We know how to convert grams into moles. So I just need to turn my 68.0 grams of water into moles, right? So I've got like 18.02-ish. And that will give me 31.52 moles of H2O. So that's what I get to use here, right? Now I'm just going to I'm plugging stuff in. So my Q equals apparently 31.52 moles is the substance I'm talking about. The C that I'm going to use, my heat capacity, I need to look over here and decide which one I'm going to use, right? Because I'm using water, so I know I got H2O. But if I look at this, I see 3 entries for water. And this is a really important thing to notice, right? That the heat capacity of solid water, ice, is different than the specific heat of solid water is different than the specific heat of liquid water, which is different than the specific heat of gas, of water in the gas phase. So we need to pay attention to, well, what phase are we in here, right? So I need to just kind of double check my temperature. If I go up here, I see that my temperature is 20 degrees Celsius to 50 degrees Celsius. And I should know that, water freezes at 0. It's liquid until you get to 100 degrees Celsius, which is where it boils. And that's like the definition for Celsius. So I know that this is liquid the whole time. So that means I'm going to select this value. Since I have liquid water at these temperatures, that's going to be my specific heat for water. So I'm going to put that in as my C. So I've got 75.3, and the units it told me were joules per mole degree Celsius. And then my delta T. Now I got to figure out my delta T. My delta T, apparently, right? So remember that always your delta T is T final minus T initial, or in other words, my final temperature was 49.9, right? Because it said it went from 20 to 49.9, and my initial was 20.0 degrees Celsius. So that means my delta T must have just been 29.9 degrees Celsius. So I put that in there, 29.9 degrees Celsius. And then I just solve. I just pop this in my calculator. Notice that, again, really pay attention to these units here. My moles cancel, my degrees Celsius cancel. I'm left in joules. So that means I know that my answer is going to be in joules, not kilojoules, not calories, not kilocalories. And that should be 7.10 times 10 to the 4th joules. Or if you wanted to convert it to kilojoules, just so you have a more manageable number, you can. And one thing I want you to notice here, right? Please notice that here my Q is a positive number, which means that this was absorbing energy, which should make sense, right? If I'm taking water, I'm going from 20 degrees up to 49 degrees, I'm heating it up. We should be able to mentally check that and be like, oh yeah, I'm heating up water. That means I should be absorbing energy. That means having a Q that's a positive number does make sense. We will see that we'll have negative Qs also. So this absorbs energy, it's endothermic. This all makes sense. So here's how you'd approach this type of question. How about this one? Again, not a phase change, temperature change. Temperature. How much energy is released when the temperature of 14.20 grams of water is cooled from 231 degrees Celsius to 198 degrees Celsius? So I'm going to use my same equation here where I have my Q equals my number of moles times the specific heat times the change in temperature. And I have to do some of the same processes that I had before. So I'm given grams of water, but I want moles of water, so I have to convert that. So 14.20 grams of water. I said 18.02 grams per mole. That ends up being somewhere around 0.7880. Check. The heat capacity, I got to go find my heat capacity. Actually, let me write this. Let me get this together. So, right, Q equals, I found my N. We'll go ahead and write that down. 0.7880 moles. My specific heat, I need to go find it. Again, I need to pay attention to, right, what phase, right, I've got water, water, water. Am I solid, liquid, or gas? I need to look at these temperatures here. These temperatures are pretty hot, right? Remember that when you get over 100 degrees Celsius, you've boiled the water. So it must mean that we are in the gas phase, right? Because we're over 100 degrees Celsius. So that means I'm going to use this bottom one now, because this is steam we're talking about. It doesn't say steam anywhere. It doesn't say gas anywhere. But if that's the temperature for water, then for the H2O, then it must be over. Then you must be in the gas phase because you're over 100 degrees. So that's going to be my specific heat. So we got 33.6 joules per mole Celsius. And then again, I need to figure out my change in temperature. I'll do that over here. Delta T, again, final minus initial. My final was 184. My initial was 231. And so my delta T is going to equal negative 47 degrees Celsius. And notice that I still had my final value was the 183 because it says that's where we went to. My initial was 231, so that just automatically spat out a negative number. And I'm going to keep that negative number. That's fine, negative 47 degrees Celsius. That's okay. It's okay to have a negative change in temperature. And then I'm just going to solve this, right? Again, make sure my units all cancel. Yes, moles cancel with moles, degrees Celsius, degrees Celsius. That's going to give me joules for my answer. So my Q is going to equal negative 1,244 joules, or in other words, I could say 1.24 since it can only have 3 sig figs, right? Or you could have said 1.24 kilojoules. Now, again, just like the other one, notice that here my Q, negative. My Q is negative, which means we release energy, which means we released energy, so it's exothermic, and that should make sense, right? So exothermic, I'll write it this time. It's exothermic because you were hot at 231, and then you cooled down to 184. How did you cool down? You released that energy, you released that heat, which we said before has got to be a negative value. So my Q ended up just automatically being negative because I took a positive number, and multiplied it by a negative number, so that gave me a negative value for Q. So my Q here was this negative value. So we're just kind of plug and play, but you just got to make sure you're in the right units and that you're doing your delta T right, your final minus your initial right. But let's tweak this. Let's find a different part of this equation. So you should probably take pause, see if you can do this. So same equations, but you got to solve for something different. This is saying that if 30.7 grams of ethanol at 22.1 degrees Celsius absorbs 369.1 joules of energy, what will the new temperature be? So I'll start you off with the fact that we are going to use the same equation, Q equals NC delta T. Here's your table of data over here on the right. It's got ethanol on it. So why don't you pause and see what you can do, because we're going to have to solve for something in the delta T thing. See how far you can get. Okay, so for this one, let's put in what we know. Q, I actually know my Q. It says that it's 369.1. And what you want to be mindful of is what's the sign of it. It says that it absorbs. So we know that when things absorb, that means it's a plus value, right? That it's a positive value. If it said, if 30.7 grams of ethanol at 22.1 degrees Celsius lost 369.1 joules, then we'd know that that was a negative value, that it would be negative 369.1. But this says absorb, so for my Q, I'm going to leave this as a positive number. I'm going to leave it as a positive number because we're absorbing, so I know my Q is positive. And then I need to start filling things out. N, what is N? Well, I've got to, right, convert my 30.7 grams of water, grams of ethanol, not water. Ethanol's molar mass is, you can just, you probably could have just Googled this, what its molar mass is, since you probably don't know off the top of your head what ethanol is. That's totally fine. But that ends up being 0.066. That's kind of creepy, but we're going to go with it. Moles, so that's what this N is going to be, 0.666 moles. The heat capacity, well, apparently the heat capacity, I've only got, or not heat capacity, the specific heat. Here's the value for ethanol as a liquid. I'm going to use that, and ethanol is a liquid at 22 degrees, so that's sound. So I can use my 113.1 joules per mole degrees Celsius. And then I'm just going to leave for now this as delta T, and we'll come back to that. We'll come back to the delta T. So I'm going to solve for everything, right, which means dividing the 0.666, dividing by 1131, so I can get it over on the other side. Which means my delta T is going to equal, if I moved all that stuff over, 4.90 degrees Celsius, right? And again, I just got that by maybe I should write it. What I basically did was I just divided by 0.666, and I divided by 1131 on each side. All right, just your basic algebra stuff. All right, so I just divided both sides by those, so I got everything. So I was able to isolate my delta T. But we want to remember that that delta T, right, means the final temperature minus the initial temperature. And I actually know one of those, right? I already know one of those. I already know that the initial temperature, right, it started at 22.1. So really, I can say that we've got 49.0. The T final, I don't know what the final temperature is, but I do know that the initial temperature is 22.1 degrees Celsius. So to isolate the TF, I just add on both sides plus 22.1 degrees Celsius. And I get a final temperature of, let's see here, 27.0 degrees Celsius. And that would be my answer. The final temperature would be 27.0 degrees Celsius. Again, to double check yourself, this temperature is higher. The temperature went up, right? It started at 22, it went up to 27. Does that make sense if you absorb energy? Yes, right? If you absorb energy, your temperature should go up. If you release energy, your temperature should go down. So the sign and that value makes a lot of sense. You just want to make sure that you're arranged everything right in your head. Let's do one more, and then we'll stop. Here's a different question, right? So if it takes 920.4 kilocalories of energy to raise the temperature of a 5.09 gram block of kryptonite, 4.62 degrees Celsius, what is the specific heat of kryptonite? What is the heat capacity of this piece of kryptonite? Right, because again, the specific heat will be true for all kryptonite, but the heat capacity is referring to this specific object. So let's do the specific heat first. For the specific heat, I'm going to use the same or a similar equation. Since I'm solving for the specific heat, I don't have to have it in grams or moles. So I'm going to save myself a little bit of work here and just go ahead and use the mass because I'm given mass, right? It says grams up here, so I'm just gonna have report my specific heat in terms of grams. And we've got our heats, right? It says 90.20. So 90.20. Where did that come from? 920.4. Sorry, it's late in the day. I'm getting tired. Equals the mass, which I already have, right? They just flat out gave me the mass. The mass was given here. It just says it was 5.09 grams. We're looking for the specific heat, and I know what my dT is, I know what my change in temperature is because they told me that this is my change in temperature, right? You're saying you're raising it, right? It says to raise the temperature 4.62. That means my delta T is positive 4.62 degrees Celsius. Now, if it said it lowered the temperature 4.62, I'd do a negative 4.62, but it said it raised it, so it's a positive value. And then I just solve for C. So I'm going to divide both sides by 5.09 grams and 4.62 degrees Celsius. That cancels, that cancels. So now my specific heat, little c, it's supposed to be a little c, is going to equal 39.1, and then I keep all my units, right? So apparently I have kilocalories up here over grams times degrees Celsius. That's my specific heat. All right, little c. And notice again that it's like the other specific heats in that it has a energy value. Here I have kilocalories instead of joules. It has an amount. Here I have grams instead of moles, but that's fine. And it has a temperature, which is going to be in C. It's almost always going to be in degrees C. Now, if I want to do the follow-up question, which is what's the heat capacity, now I'm just doing Q equals big C delta T, and I can use the same values that I had before, right? I had 920.4 kilocalories. I don't know the specific heat, that big C, but I do know that the change in temperature is still 4.26 degrees Celsius. So I'll divide both sides by 4.62. So those cancel out, and I get that my big C is going to be 199 kilocalories per degree Celsius. And that's exactly what a heat capacity unit-wise should look like. So the heat capacity, right, is just saying that it takes 199 kilocalories to raise this hunk of kryptonite 1 degree Celsius, is what it's saying. So here's all the different possible types of questions you could be asked about specific heat and everything, right? You can solve for the energy that's being transferred, the Q. You can solve for the amount. I didn't do one of those. You could solve for the M or the N, right? You could solve for the amount. It's just algebra. You could solve for the heat capacity or specific heat like I did in this one, or you could solve for the change in temperature like I did for the one before. Definitely practice this one, right? Do your practice problems, practice so that you could get used to seeing these types of questions. And what we're going to do in the next video is I'm going to show you how to combine the change in temperature with the change in the phase. So like if you have like a cold block of ice and you warm it up to 80 degrees Celsius, you're going to heat that ice from like -20 up to 0. Then you got to melt it. Then you got to heat it up to 80 degrees. And so you're actually going to use both of these types of equations, the ones from this video and from the previous video. So keep an eye out for that. Again, study up, practice. Good luck.